Hello everybody. In this video, we're going to talk about the compressors as one of the components that we have in the pressure changers. And the problem that we're going to solve today is just an air compressor. So we have here air as the component, and this might not be a very well known information that you can define air as a component that's already there in the software's data bank. So you don't need to define it as oxygen and nitrogen, just air if you are using it as air. So I mean you're not using it in distillation to separate oxygen from nitrogen, or in a reactor that will react with oxygen or nitrogen alone. So you're dealing with them as a package as air, so you can put it as air. And you can find all the information and all the details about the air, the physical properties, and the density, viscosity, critical temperature, critical pressure, boiling point, and all these stuff are available here if you are interested in finding them. Since we are doing compression and we are gonna work at high pressures, we're gonna use any cubic equation of states. You can use Penn-Robinson, you can use SRK, you can use Lee Kessler, whatever. They're all gonna give very close results. So let's go and see what we're gonna do in the simulation. So I'm gonna define the feed stream, which is, as we said, I'm gonna call it feed, and as we said, it's just pure air. I'm gonna start at ambient conditions at 25 Celsius and 1 atmosphere. I'm gonna make it like 1000 kilomoles per hour, and the mole fraction is 100%. So this is done now. We know all the information about the feed stream, and let's see what we have here. We need to have or add a compressor, and once we add the compressor, we need to connect the feed stream. It should be a well-known piece of information that the feed stream to the compressor enters on the large area side, and the product comes from the small area side. And this kind of indication that the feed is being compressed. So I'm squeezing it and I'm reducing its volume, so it's going from the wide area and coming out of the small area. So I'm gonna connect the feed stream here and connect the product stream here. And let's see what will happen when we open the compressor. So I'm gonna find that we have three three parts where you should add some data or define the compressor in. The first is to define whether to deal with it as a compressor or a turbine. And both are kind of equipment that deal with gases or vapors, but they work the other way. So the compressor, in case of compressor, you provide work, and this work converts converts into the compressor or into pressure. So you are increasing the pressure of the gas by applying work to the gas. But in case of a turbine, you do the opposite. You have a gas stream at high pressure, and it passes by the turbine. The pressure decreases, and power is produced. And that's why you would notice here in this part, if you're choosing the compressor, then you have the option of discharge pressure, pressure increase, pressure ratio, and the power required to do the compression. In case of a turbine, you'll find that you have pressure decrease and power produced, and this is how they both work. Um, You'll find here another list that you have to pick something from, and this is how you are going to do the calculations. So you can either choose to have it as an isentropic compressor. You can use it isentropic compressor using ASME method or using GPSA method. They're just methods for calculation of the pressures and temperatures and all the physical properties through the compressor. Or it's mainly about the relation between the inlet and the exit pressures and temperatures, and from this you can find all the other physical properties. You can use a polytropic compressor. You can use it with the GPSA method. So you can have it as a positive displacement compressor, Anyway, so I'll go for the simplest case, which is the isentropic. Isentropic means it's adiabatic, and it is at constant entropy. So there is no change in entropy by compression. Of course, this is an ideal case, but this is a simple case to calculate, and that's why we are gonna work with it right now. And then we will see in the next cases how it works. Again, I'm interested in doing this first because I'm gonna show you how the calculations can be done manually, so we can compare our manual results with the results that we get from the software. Um, Here you can choose either to go for the discharge pressure or pressure increase, pressure ratio, power required. I'm gonna go for the discharge pressure. I want it to be 10 atmospheres. And here you don't have to define the efficiencies. Because there are some default values that will be used if you do not provide yours. So here in the isentropic efficiency, it tells that it's you have to define a fraction between 0 and 1, or 10 to the minus 15 and 1. But its default is 0.72. So if I don't put any value here, it's going to be taken as 0.72. The mechanical efficiency is similar, but its default value is 1. We can run the simulation now and see what we get. The point that I want to highlight and keep your attention to, or draw your attention to, is the relation between the pressure and the temperature. I'm starting with the ambient conditions of pressure of 1 atmosphere and temperature of 25 Celsius, and I'm just compressing. I'm not putting it in a heat exchanger. I'm just compressing up to 10 atmospheres. And when we go to the results and see how the output is, so the output, you'd see that this is the horsepower that you need, the brake horsepower, the efficiencies, again, it's 0.72 and 1. The outlet pressure is 10.13 bar, which is 10 atmosphere. The outlet temperature is 402 degrees Celsius. And it tells that the isentropic outlet temperature is 299.6, it's around 300 Celsius. This is in case of 100% isentropic efficiency. This is using the 0.72 isentropic efficiency. So it increases the pressure more, and this is because the ideal case is not actually taking place because of this efficiency. Anyways, so let me just show you what I have here. So these are the equations, are the relations that we know about the isentropic compression. It's a relation between the T2 and T1, P2 and P1, and gamma. The gamma is the ratio between the Cp and Cv, the specific heat at constant pressure and specific heat at constant volume. And you can see that the T2 is function of T1, and T2 increases as the P2 increases. So this agrees with what we just said. And regarding gamma, we know that gamma is the relation, or the ratio between Cp and Cv, and we know the value of gamma for some cases. So we know for monoatomic gas, we know the value of gamma. We know it for the diatomic. So in diatomic, it's 7/5, so it's 1.4. And so on. So I know the value of gamma, and here I put and provided the inlet condition 1 and 10 atmosphere, and this is in Pascal, and this is the inlet temperature of 25, and this is in Kelvin, and this is the outlet temperature that I calculated using this relation. So from this relation, based on 100% isentropic efficiency, the outlet temperature is 302.5. It's calculated here as 299.6, so it's around 3 degrees difference between the what I calculated and what Aspen Plus calculated, which is a very, very good agreement actually. In case of efficiency, the calculations would be more complex, and in case of using polytropic compression, it's gonna be again more and more complex. So in the results, you'd see that the values change a lot. It was around 400 and now it's 450. So we have a big change in the or some change in the outlet temperature in case of the polytropic compression. Um, there's one thing that is important that I want to mention in this video as well, which is related to what we were just saying. In case of, let's say that in case I have this as a turbine, and in the turbine I would make the feed stream at high temperature. So I'll reverse, I'll make it 10 atmosphere, and to make the outlet pressure of 1 atmosphere. So in this case, I am doing it the other way. I am reducing the pressure, and I'm starting with a low temperature. So I'm starting at 25 degrees Celsius, and I'm reducing the pressure. So I should expect the other or the opposite to happen to what the opposite of what happened in the previous case. So I, instead of increasing the temperature, I would decrease the temperature, and this is what we'll see in these results. I have the outlet temperature or pressure 1 atmosphere, and the outlet temperature is negative 154, almost 154 degrees Celsius. And this is actually, and this is why I did this this tutorial, because this is how refrigeration cycles work and how refrigerants work, and this is what happens in the fridge at home. This is how you can get the temperature very low, even might be like 40 or 30 degrees lower than the ambient temperature. And this is because the refrigerant, which is the Freon or whatever its name, is being compressed using this compressor, and this is what consumes the energy in the fridge or in the freezer. Is the compressor that applies, you're applying a lot of work to compress the liquid, and then you suddenly throttle, or the liquid is being throttled suddenly, and this results in a very increase or very big drop in the temperature, and that's why you can get the freezer to work. So it's this compressor or compressing throttling system, it provides a continuous source of cooling, regardless the outlet temperature, regardless any conditions around the fridge or the freezer. It's gonna work anyways. So this is important to understand that, and this is again what happens in the industry. If you're working, in case people are working with cryogenic systems, or you're working with anything like it's very crucial in cases like liquefied natural gas, and in such cases, because these industries require the natural gas to be stored at very low temperatures. So there is no way you can do or achieve these temperatures without having the refrigerants and refrigeration cycles, of course. So I hope this video helps, and I'll see you in the next video, inshallah. Goodbye.